first came out, and I realized that that would be the dream. It would be to use computers to make film. My mom saw an article in the New Yorker about digital domain being started up by James Cameron, Scott Ross, and Stan Winston, sent me the article and said, hey, you should go apply to this company. And so I did, and had a very interesting interview with Scott Ross. And a month later, I was in Los Angeles unpacking boxes.
I didn't understand how much your PhD was involved in computer vision. And then here you are all the way to now. Why don't you tell us what you're working on now? Because it really ties straight in.
I hadn't even thought about that. I really haven't. My career has been fairly focused on what I started with, and I continue with it to this very day. Over my career, we've tackled a whole bunch of things. DD was the original author of Nuke. Eventually, sold it to the Foundry. We did computer vision stuff. We've done fluid simulation stuff. We've done volume representations. There's all sorts of techniques that you can find in Houdini that originally started at Digital Domain. That's been what we've been doing. We've got a really cool program for doing hair called Samson that has been the product of a lot of software developers. Right now, Gene Lin is leading that up. And we have muscles and skin simulation that David Miner and Michael Ewert are writing. And then we have all this stuff for doing facial animation and a real-time simulation of humans. This whole project is being led by Darren Handler. And some of our software developers like Lucio Moser and Mark Williams are key contributors to this. And we have just done a brilliant team. Melissa Sell is leading up a lot of the real-time aspects of it all. And you can kind of see there's all this intense focus on hair, muscles, and skin, and facial performance, and how the character moves. That led to the TED Talk that I did, where I was controlling a digital copy of me alongside me. And now we are working on creating that kind of quality, even better quality, that can talk on its own. So it's an autonomous character that you can tell what to do, and it will talk to you and interact with you. It's extraordinarily fun. And I'm telling everybody in this the software team, you don't have to use machine learning. Sometimes just a direct program will solve the problem that you're trying to solve. But often machine learning can really make difficult things less difficult, or difficult in its own way, let's say. And all of this stuff is like, okay, it's science. Here's something your face is this physical object that we want to model, and we want to try to understand it in one way or the other. But then you take machine learning and you say, well, hold on. What if we were able to train something where we just showed it a lot of faces, a lot of how somebody's face moves, and instead of trying to figure out all the volume-preserving physics of what's going on in a muscle that controls how your cheek raises, we'll just let the machine figure it out after looking at thousands and thousands of example poses of your face. Of course, that's its own kind of difficulty. You have to collect and make sure all the data is correct. But then you literally kind of just press a button and let the computer just sort of spin on how the face moves, and all of a sudden you've got this thing that can move the face more realistically than any kind of physical simulation. And it changes the way you look at how to solve problems. I'm just going to gather 10,000 frames of somebody's face moving and then let the computer come up with a model on its own. The MASQUERADE 2 process that we've developed makes it really easy to take facial performance, capture it, process that capture, which used to be a pain in the butt, and then create digital characters that look like the person that was moving it, all in one shot. It's a very smooth pipeline. well, there's a certain number of shots of Thanos, and I don't know the exact number, but it wasn't huge, right? It was, he was on screen for a lot, but it wasn't an enormous amount. We're doing projects now with 30 to 40 hours of motion capture, wow, which is multiple characters, just hours and hours and hours, and where 40 hours of a character doing things. Now, this is for video games, but it could be for film, it could be for anything. You can have these characters now that the process of capturing the performance and taking it to a digital character is no longer the barrier. It's not, okay, we've got 4 months and we'll have you something. Now you can just start the pipe and, okay, here's an hour of performance, here's another hour of performance, here's another hour of performance. We are addicted to big GPUs right now, but big GPUs are expensive. And over the years, our render farms are filled with a lot of CPU power rather than GPU power. By and large, new computers that we're buying actually have GPUs in them, even if they're just meant to be on the farm. And this applies not only for machine learning, but also for the latest renderers, right? The amount of speed that you're getting using GPUs to do the rendering, whether it's V-Ray or Redshift or RenderMan or anybody, they all have GPU acceleration. How Nvidia is dealing with all this. Of course, they talk about their GPUs and the number of CUDA cores that they have and the amount of compute that each one of the GPUs comes up with. But also, like you said, it's the whole enchilada. There's this huge lake of data that you need to get into the GPU. And so the computers that are ideal for machine learning not only have some big GPUs with a lot of parallel processing capability, but they also have this pipe that you can take terabytes worth of data and start throwing it through the GPU relatively quickly. We're doing a lot of things with neural rendering, right? Where you have the machine learning process that you've created do the final stages of rendering to bring it to reality. But unlike a renderer, if you don't like the results of the machine learning output, it's really hard to change. It's like, you get what you get. I know what reality is. And if you don't like what my reality is, then tough crunchies. If you ever hear the word latent space in machine learning, that's basically this representation of what the computer knows that's somewhere in that black box. And if you can come up with a way of adequately manipulating the latent space so that you can control basically how the machine is thinking, then you've got power. And so there's a lot of research out there that says, wow, if we've figured out how to disentangle like the pose of a character's head from the latent space. And so now, instead of just getting what the computer told us the pose was, we can actually control the pose. So the autonomous character that we're putting together requires speech recognition. So if somebody is talking to our character, we have to understand what that person is saying. Speech synthesis, the character has to sound like somebody, so we have to be able to control the character. There's this conversational AI that controls the behavior of the character. So what the character is going to say, but also what the character is doing. And all the rest of the stuff. So the facial motion, the expressions, what the character is actually doing. All of this technology is new to us. Who would have used all this stuff, speech recognition, all this stuff in visual effects? It's not what we do. But now that I'm seeing what this stuff is capable of, it is actually terribly useful in visual effects. The really effective artists that I see are artists who are sort of tapped into technology, that are not afraid to use technology, and that have learned to combine technology with their art skills, the craft.